Yeah, so we'll be proceeding with looking at how the compilation works for a call to a block. And here we have code 10 times do, and then we have puts in with a block. And this is just a simple script that calls a block. We saw this example in chapter 1. So the interesting bit about this code is, of course, the block, which is what we'll be focusing on later on. So we have figure 2.9, and this is the AST tree for this code. So just like before, we have the node scope, and then we follow to node iter. So after node iter, we are going to have a branching arrow that takes you to another, I could say section with node scope. And then we also have another arrow that takes you to node call. This is a method call. The specific method is the times method. And then node literal. Remember I talked about node literal being anything from, now let's say, an integer. And then in this case, the integer is 10. So this looks very different than the example we saw earlier, which is puts 2 plus 2, mostly because of the inner block shown at the very right. And the author proceeds to say that Ruby handles the inner block differently, as we'll see shortly. So, like we mentioned before, what we are trying to do here is that for every AST node, it's going to be converted into its own set of YAV instructions. And going by that logic, we start with node scope. And then following node scope, we'll go to node iter. So at this point, there is still no code generated. But notice in figure 2.9 that two arrows lead from node iter. One to node call, which is the method call, the times method. And this represents 10.times call, and another to the inner block. That is the second arrow that slants in like a diagonal fashion. So the diagonal one leads to the inner block. The one that proceeds down below takes you to the method call. So one thing to note is that Ruby will first continue down the AST tree, and the arrow that takes you all the way down to the node call will be taken, as opposed to the one that takes you diagonally. So after node iter, you'll proceed to the node method call, in this case the times method, and following this, node call will later take you to node literal, because remember we had node literal at the very end, which is the integer 10. So at that point, we'll put the number 10 onto the stack. As you can see, put object onto the stack, and that is 10. And then we will send the times method, or the times message, because method and message are interchangeable. We'll send the times message to the receiver, which is the 10 we've put onto the stack trace. And as you can see here, we have the arguments being 0, simply because when we are calling this method, or when we are sending this message to the 10, to the receiver 10, we are not specifying like a literal argument, but rather passing in a block. And that is why you see that argc is 0, while block is also specified by block and then colon block, to show you that when you're sending this message to the 10, a block is passed in. And the block is, of course, the argument to that method call. So now proceeding on to the part of the inner block and how Ruby compiles it. So Ruby continues by compiling the inner block, beginning with the second node scope. This is the one you can see here, shown at the right in figure 2.9. Figure 2.13 shows what the AST for that inner block looks like. This looks simple enough, just a single function call. This is the function call. The related method is the puts method, and a single argument n, because remember we pass in n as the argument. So you can see at the very bottom that we have node dvar, variable id is n. So notice the value of the table and args in node scope. Initially in the example of put 2 plus 2, these values were not the same as what you see here. They were similar to what you see in figure 210, whereby you have table being equal to none and args being equal to none. But then when you look at this example of the block, we have table being equal to n, and then we have the arguments being equal to 1. So notice the value for table and args in node scope. These values were empty in the parent node scope, which is the one on the left. No, on the left when you try to extrapolate this diagram, but they are set here in the inner node scope. As you might guess, these values indicate the presence of the block parameter n. Also notice that the Ruby parser created node diva instead of node lit, and this is because node diva is pointing to a variable as opposed to node literal, which could point to now, for example, like an argument, as we've been seeing all along. So this is the case because n is not just a literal string; it's a block parameter passed in from the parent scope. Figure 214 shows how Ruby compiles the inner block. Nelson, I don't know if we should go through this.
I think I think we can safely skip this part. This is
Yeah,
more detail, uh, but
yeah.
we it's okay.
We can just skip it.
Yeah.
Okay. So yeah, and now this will be the final you have instructions that we see after compiling the main method call, that is 10.times, and then as well as the block. So I went through the YAV instructions for the first part, whereby you put the object 10 onto the stack, and then you send the times message to it. And then for the YAV instructions, you put self, just like we saw in the example of puts 2 plus 2. So you put self because when you have puts, you hadn't specified an explicit receiver. So of course, the current self will be the receiver for that puts message. And then get local to, I'm not sure what this means. Nelson, I don't know if you
Um,
could get local.
I don't know what it means either. Since I it's is it just the current value of n?
The what?
Is it just the current value of n? So-
No. Oh, actually, I think this relates to, this is an index for the local table.
Oh, okay.
Yeah, yeah. The very last part of the chapter. I think this is used to refer to that variable, if if I remember correctly. So opt send simple, we looked at this. This is a specialized instruction for the common puts operation. I don't know if Nelson, there's any question on your end, because I'm done with that part.
Yeah, I mean, the what bothered me was the if uh, I had assumed that the table was some sort of array because of the syntax in the first part, and it's called a table. But it might not be because the value of table was n. and not an array containing a single element n. If you scroll up,
Here.
yeah, but you're so node scope table n. You see how at the top it says node scope table, and then the brackets, and then it says none.
Yeah.
I had assumed the brackets meant that it was just like an array of items in a table, and maybe it is because we said get local is of index 2, but
Yeah.
I don't see usually indexes are zero based. So it would start at 0 and then go to 1 and then go to 2, which would imply that there were 3 elements and that we were getting the third element from some array, but that
Oh yeah,
doesn't seem to be
actually,
the case.
mm, actually, when you mentioned that, I think when we reach that section of the book, most of those indices start at two. I don't know why that is, but most of them they start at two in like those examples. And I don't know if you can see my screen. You have this example,
Hmm.
and you're saying that it's two here, right? Here. And
Oh,
then you see get local is two as well. So when you proceed to now another example, and this is one with a method now, you see that it still starts at two. Yeah? And then three, and then four.
maybe, okay, so maybe 0 and 1 contain some sort of metadata on that table. So scroll up, because there's like a line ID. Not this page, keep scrolling.
Okay.
So, okay, so, right. Uh, so 000 trace, you see in the middle of um, the output of this assembly, it
Which,
has 000.
yeah, yeah, at the very left.
Yeah, at the very left. So
Mm.
maybe the table contains uh, like the line number and then the command or the instruction.
Yeah, maybe I don't know, but that is just something I noticed. Most of them they don't start at zero or one. They start at two throughout actually throughout up to the end of the book. That is how it is.
Oh wait, so there's it there. I can see in this disassembly, local table, size 2, arg 1, options 0, rest -1. Yeah, I'm still a little confused by these tables, but
No, the pattern.
I don't think it matters
Mm.
because that gets into the implementation. Um, I think it's just enough to know that uh, it is whenever you're dealing with blocks and you need some sort of context, the context is stored in the table, and we're able to get the values out of the table. Um, so I think it's just enough to know that amount of information. I think, I'm confused by the implementation. And honestly, the implementation could have changed between when this book was written and today. It's been more than
Eh,
10 years. So, um, so yeah, we have this block thing that is that needs a context, and the context is stored in the table.
Yeah, so um I think now we'll just proceed to the displaying YAV instructions.
This still works, by the way. I don't know if you tried it.
Yeah, yeah, I tried it. I actually have like an example here. I don't know. Let me see. Let me see. I have an example here. I don't know if you can see.
Yeah.
Yeah. So put this is the code I was trying to run.
Hmm.
This is a is equal to 2 plus 3. Yeah.
Hmm.
And then, of course, here you have the local table, you have size 1, args 0. So these opts and then the rest and then the pods, these are related to arguments. We'll be looking at them like later on. And I'm not sure about what the negative one means for the block, because this is not really related to blocks. I'm not trying to like evaluate a code block, so I'm not sure about that. But the
In
opts and the post, that is what they refer to. So what I was trying to see here is that whole stack based virtual machine thing whereby you put an object 2 onto the trace, then you put another object 3, then opt plus. So you have here call, and then you have the bang, and then you have the method ID. Here it's the plus method, and then the argument is 1, of which the argument will be 3, and you have duplicate, and then duplicate is like you get the value of the opt plus, so you'll have 5, and then when you duplicate that, you use set local to assign the 5 to a, so that you can have 5 returned to you. So that is just what I was trying to say. I don't
yeah,
know if it.
that duplicate. I didn't know that dupe was duplicate. Um, I actually didn't know what it stood for. Was that in the book?
No, 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 no. This was just me trying to see what it returns.
Hmm.
Yeah. So I don't know if that clarifies a few things. And then I think leave is similar to return.
Hmm.
Yeah, leave is similar to return, like the same way you use return inside like a method, and then you end the method at a certain point. It's similar.
Yeah.
Yeah, and
Yeah,
then
that makes sense.
another thing is, I don't know if you can see here at the very start below the statement local table, you have a, and then you have the at symbol, and then you have 0. Yeah?
Hmm.
Yeah. So you can see that that is referenced by set local to assign the 5, which was the value of 2 plus 3 to a.
Hmm.
Yeah. So that is also something to note. But yeah,
Yeah, so
that's
so that it looks like it's the variable name followed by at. Maybe that's some index in a table, like at zero, at the zeroth index.
yeah.
Maybe.
But yeah, it's definitely the variable name, because the variable
Yeah.
name was a. Yeah.
Yeah. Great.
So can you still see my screen for the book?
No, you need to
Yeah.
reshare.
Yeah. So that is really how you display the YAV instructions. Also, another thing I would like to point out is that the whole node scope and node lit and node, okay, all things that start with node underscore, most of those things were phased out.
Okay.
Yeah. So you might, for example, for the case of node literal, you might see something like int when you try to run your code through Reaper, which is a tool we saw in chapter 1, and I think you had mentioned that. So yeah, displaying, you have instructions, you have code is equal to less than end, and then end So the code is puts 2 plus 2, and then you pass the code into this Ruby VM instruction sequence dot compile and then dot disassemble. So this will be the output returned to you. And here you can see that you have put self, because remember you didn't specify an explicit receiver for the puts method. So that will be the first put self, and then you put object 2 onto the stack, put object 2 onto the stack. The first two is the receiver, the second two is the argument, and then you perform the operation, which is the plus operation. You see that method ID is plus, and then finally you use opt send simple, and then you leave, which is similar to return.
When you say that the node things were phased out,
Yeah.
what node things are you talking about exactly? Because I thought you were talking about the VM instructions here. Um, node
No,
scope.
what I'm talking about is this. Like if you were to, now let's say you have this AST tree, this AST trees we've been looking at, yeah.
Yeah.
So instead of node literal, like you see here in this example, if you were to try to see and to run this code through Reaper, the Reaper we saw in chapter 1,
Oh,
this is not what it's going to return to you. It's going to return int, which is a stand-in for integer, to mean
oh,
10
so
as
yeah.
opposed to not literal.
Okay, so the abs I thought you were okay, so I got confused between the abstract syntax tree and the compilation step. So yeah, the abstract syntax tree labels some of the nodes differently
Yeah.
now.
So that
Yeah.
is what I was referring to.
Oh, okay.
Yeah. So I think that is really pretty much it. These are just more specific examples which look at now let's say this displaying, you have instructions for a call to the block listing 211. A few things to note here. You can see that you have line number 2, which is highlighted here. You're sending the times message, method ID is times. You're sending it to the object 10. The argument specified is 0, but you see that block colon block specifies that you've passed in a block as the argument to this method. So that is one thing to note for blocks. Yeah, I'm not very sure about what all these numbers mean. The ones on the left and the right.
Yeah, I got confused as well because I they don't because it starts at 0, goes to 2, 4, 6, and so I was expecting them to increment by 2, but then you see below that 4, 5, 7, 9, 11. So
Yeah.
yeah, it was not
So
evident.
another thing maybe to note for this code block example is that, remember, we are supposed to get back to YAV instructions to, like, a pair of YAV instructions. So that is why you see that the one here, which is the global scope or 10.times, will give you the first set of YAV instructions, and then the second set of YAV instructions will be related to the evaluation of the code block. So that is also something to note in that case. And
So
let's proceed to local table.
yeah. I mean, one other thing that I can think of is like in the Intel instruction set, you have some instructions that take up a single byte of information, and other instructions that take up 2 bytes of information. So maybe this is an index for what byte this instruction lays on somehow, but I don't know.
Oh yeah,
That's
yeah,
just a
yeah.
wild guess.
That is That no, no, no. That is the right thing. You see these numbers on the left. I've remembered. I searched it.
Hmm.
The numbers that are 0000 and then
Hmm.
0002. Yeah, I think ChatGPT mentioned that some instructions take like now let's say 2 bytes, and then others take like 3 bytes, and then others take like 1 byte. So the incrementation goes on happening like that
Okay, so that's what that
for the
is.
ones on the left. Yeah.
Okay, cool. Well, I
So
guess I guessed right.
yeah, you guessed right. So local table now, and here local table is something we looked at. I'm going to just read through the text. In figures 2.3 through 2.14, you may have noticed that each node scope element in the AST contained information I labeled table and args. These values in the inner node scope structure contain information about the block's parameter n. See figure 2.9 on page 39. Ruby generated the information about this block parameter during the parsing process. As I discussed in chapter 1, Ruby passes the block parameter along with the rest of the Ruby code using grammar rules. In fact, I showed the specific rule for passing block parameters back in figure 130 with opt block param. So once Ruby's compiler runs, however, the information about the block parameter is copied out of the AST and into another data structure called the local table, saved nearby the newly generated YAV instruction. Each snippet of YAV instructions, each scope in your Ruby program, has its own local table. So this statement means that now, for example, that example of the code block, since you have two sets of YAV instructions and two scopes, which is the global scope and then the scope of the code block, you'll have two local tables. And it goes on to show here a snippet of YAV instructions with a local table. So here you have put self, and then you have get local 2, and then on the very right you have local table, you have 2, and then you have n, which is the argument. So notice on the right side of figure 215 that Ruby has associated the number 2 with the block parameter n. As we'll see in chapter 3, the YAV instructions that refer to n will use this index 2. And the get local instruction is an example of this. So that 2 is just a reference for this block parameter in the local table. As it turns out, Ruby also saves information about local variables in this table, hence the name local table. And then the arg notation indicates that the value is an argument to the block. In this case, the n is an argument to the block. So this is another local table. Now here we have a method named add2. We pass in two parameters a and b, and then we get their sum. So here we see that here you see that Ruby lists all the three values in the local table: the sum, which is the variable, and then the argument. So you start with the sum, and then it gets the index of 2, and then b gets an index of 3, and then a gets an index of 4. And then when you move on to the right, you can see that you say get local 4, and then you use these indices to reference the variable, the sum variable, and the arguments in the YAV instructions.
This makes so much sense because for every method, it's in its own scope. Every block is in its own scope,
Yeah,
and if you create a variable in that scope, you need to make sure that it's only gonna be able to be accessed in that scope, and that no other scope, like it can't live, that variable can't live outside of that scope. And so these local tables, copying the variables that exist in that scope into this local table is a nice way to go about making sure that you limit the variables to specific scope.
Yeah, yeah. And then, of course, you can see that here we end with set local to be 2. And remember, 2 is the reference for the sum variable, because at the end of the day, we want to have the value of the addition being returned to us. So that will be the last instruction in this figure 216. And then here you have some different types of methods and block arguments. So you have arg, which we've been seeing, and it denotes a standard method or block argument. And then you have rest, which is an array of unnamed arguments that are passed together using the splat operator. And then post, and then block, and then opt. So I don't know, Nelson, if you remember, but these appeared in that example in my terminal.
I didn't remember all of them, but yeah, okay. I'll trust that they appeared there.
Yeah, the kind that if you look at them, you try to look
I
them.
don't remember the post.
No, like the code I shared is the one I'm referring to.
Oh, in IRB.
Yeah, in IRB, that's the one I'm referring to.
Oh, okay. Yeah.
Yeah, that section of local table. Yeah,
Okay.
so
We have eight
the
minutes.
following examples, we have what?
8 minutes left.
Yeah, the following examples now will try to see how the have instructions are displayed and how the local tables show up for each of those kinds of arguments. And if you look at figure 270, whereby you have this extra set of arguments which are specified using the splat operator, you can see that for C, the argument C is referred to as post. And remember here, post is a standard argument that appears after a splat operator. And then when you look at args, which is the one the extra set of arguments with the splat operator, it will be referred to as rest, which you can see here, an array of unnamed arguments that are patched together using the splat operator. And then the same logic applies for B and A, because remember these are normal arguments, so they'll have arg as opposed to rest or post. And then these other examples just look at how the local table, how the arguments in the local table will look like if, for example, you have a method whereby you have a specified value, default value as part of the argument list. And another example whereby you have a keyword argument, like for example in example 219. And yeah, I think for the most part, that's it. Displaying the local table is displayed as part of the YAV instructions. So you can just you refer to that section of the discussion. You'll have the local table first, and then you'll have the instructions displayed next. And of course, they vary depending on the code you're trying to compile. So yeah, I think that's it.
Yeah, this was definitely a dense chapter. It goes really far into detail. And I'm glad we skipped that section on the C code because it's like, oh my God, this is a little too much. If I'm not gonna read the C code, I don't know. It was just my brain went on vacation when I read that section. But yeah, this was definitely like and but the going through it with you actually helped me out a lot because there were a lot of things on the first read where I just didn't understand and I just went, okay, well, whatever. I'll read the next section. Um,
Yeah.
and I didn't read every single little output in great detail. So going back through it in with a little bit more care did help me. understand more.
Yeah. So yeah, I think that's pretty much it. So now we'll be looking at chapter 3 next week. Yeah.
Okay, sounds good.
Okay. You have a good one, Nelson.
All right, take care. See you next week.
Thank you.